are going to jump right into calculating what's called surface area. So we're going to look at a specific situation right now. We're going to look at what happens if you take a curve like this curve here, y equals f of x perhaps, and you rotate it about the x-axis, which we've done many times. Can you imagine that you get a shape that looks a bit like a pawn on a chess piece? Right? Now, we've done shapes like that, and we have rotated shapes like that about the x-axis, but didn't we find the volumes when we did those? Right. Well, now we are going to find the surface area. So the surface area would be, if you covered the outside with cloth, how many square feet of cloth would you need, right? So we're going to calculate that, and it is going to only be about the x or the y-axis. So you don't need to worry about rotating, you know, parallel to the x or parallel to the y, right? We're only going to do x-axis ones and y-axis ones. And I think it'll become clear pretty quickly why we only focus on those. It's to do with complexity. They're really messy things. Now, if you have a curve and it's written in the form y equals f of x, which is probably this one here, and you're going from x equals a to x equals b, right, from there to there, the formula for getting the surface area is the integral from a to b, 2 pi f of x, and this ugly square root. If I cover up the first part of that, do you recognize the square root of 1 plus the derivative squared? Do you recognize that? Yeah? Isn't that the arc length formula? And do you remember there was a formula, right? You know, remember the 2 pi f of x thing that you did in one of the versions of the volume? Isn't this formula a little bit like an arc length formula and a volume formula kind of mashed together in some way, like a Frankenstein formula? You just need to memorize it, write it down somewhere, because you're going to be using it a lot, right, in a little cheat card, so that when, you know, it's a surface area question, you bring out the formulas. Now, you would expect that that was the only formula that you need for rotating a curve about the x-axis. But sometimes the curve is not given as y equals f of x. Sometimes the curve is given in the form x equals a function of y, like x equals y squared. Now, if you want to visualize what that might look like is, can you imagine that you're doing a curve that goes from here to here? And this is c, and this is d, and this formula is called x equals, you know, y squared minus y, right? But it's still getting rotated about the x-axis. So you can imagine what that shape might look like. It would look like a bell, probably, right? So if you are given information that is in the form x equals a function of y, and it's from y equals c to d, so from here to here, right? And you rotate it. Notice that the formula is 2 pi y, the square root of 1 plus the derivative of y squared dy. So there are now two versions of the same problem. Rotating a shape about the x-axis. There's the version where everything uses x's, and a slightly different version where everything is using y's. We cool with that? So if you see a question and it's y equals x cubed from x equals 1 to 5, and you're rotating on the x-axis, use him. But if it's x equals y cubed from y equals 2 to 7, again, still rotating about the x-axis, you use this one. So what we're really going to do is as much practice as we can, because these darn questions take forever and a day to do. They are long. And we'll see if we can, you know, just get practice at doing them. Before I do that, these algebras, doesn't matter which one, you tend to get three main things that you end up with. This guy inside the square root ends up being a perfect square. You have seen lots of them in arc length, right? So the guy inside the square root ends up being a perfect square. That's very common. Also, even more common, I would say, is that you end up using a u sub to solve these. And the third version is pretty sparse, but occasionally it happens that this square root ends up cancelling in some way with the other one. It ends up being a nice piece of algebra. But that third situation is maybe the least common, although it does happen. So let's jump in with an example of a question. And yeah, let's do it from start to finish. This is a version of question 5. And we are being asked to do a very simple curve. Can't get much simpler than that. We're going to do it from x equals 0, say to 2. And we are going to find the surface area of that shape. Now, if you wanted to sketch it, it would look something like this. There's 0, there's 2. Can you imagine it would look a bit like a curved cylinder? Curved cone, I mean, right? Oh. Excuse me. This is an axis, this is an axis, and we're being told it's rotated about the x-axis. So I know I'm going to use the top formula. So it's going to be the integral from a to b, 2 pi f of x, the square root of 1 plus the derivative of this squared dx. Are you happy about where all the pieces of this formula came from? Right. There's f of x, there's the derivative of it squared. There's the start and finish, and it's in terms of x. Now this fella becomes the integral from 0 to 2 pi x cubed, the square root of 1, 9x to the 4 dx. Next line, I'm going to pull out that 2 pi. What method do you think I'm going to use to integrate an x cubed square root of ugly guy? What technique will we use to integrate it?
Use of.
Agreed. What would the use of be?
Would it be the 1 plus 9x?
Yes, it would be. So, wouldn't this be a pretty standard one? You know, ugly thing inside square root is the u sub kind of rule, right? So if we differentiate this guy, we get, I believe, 36x cubed. If we do the crossover, we get 36x cubed dx. And if you divide both sides by 36x cubed, you isolate the dx, and I've had to squeeze it in due lack of space. I'm pulling out the 2 pi. I'm going to do an x cubed, a square root of u, a 1 over 36x cubed, and a du. And the x cubed cancel, and if I pull out that 36, I now have 1/18 pi. Would you agree that that is a very nice integral? Right, so the u sub saved us, because the x cubes cancel and the 36 when you bring it outside, and the 2 gets you 1/18. If you want to integrate something like this, you would call it u to the power of half. That means we can now do the power rule, which is essentially add 1 to the power and then divide by the new power. If I tidy up these fractions, the 2 and the thing gets me now 1/27 pi. And the u to the 3 halves, I'm going to rewrite it as that guy. And return back to the x's. And at this point, I can evaluate it at 0 and at 2. If you plug in 2, you get 2, 4, 8, 16. I have no idea what 9 times 16 is. I don't want to risk it. It's 144 plus 1. So it's the square root of 155 by the way, cubed, almost missed that. Take away, if you plug in 0 here, you get nothing. 1 plus nothing is 1, cube root of 1 is 1, you get 1. And I should try and make it look as pretty as possible. So 155 cubed inside the square root gets you 155. The square root of 155, take away 1. And I don't think I can do any more than what I've got. So that guy is the area of the surface of this guy, x cubed. Are we comfortable with the process? So let's make another one. Let's make it uglier. So it didn't take long for me to find an uglier one. Y equals the square root of 4 take away x. And x is going to go from 1 to 4. So far, so good. Oh, and it's going to be rotated about the x-axis. Now that means I'm going to use this formula, but when the equation, the y is ugly, I tend to find the 1 plus derivative squared first. So this guy has to be rewritten in a format that's going to make derivatives easy. So I'm going to call it a half power. I'm going to then differentiate it. 1, right, multiply by the power, so 1/2 times this guy, reduce the power by 1. That is not 100% correct. What have I missed that's meant to go here, right where my finger is? 4 minus x to the half gets you a half. 4 minus x to the negative half times something else.
A -1.
Agreed. See if that was minus 4x when you do a minus 4, and if it was 2x, you do a plus 2. So there's a little negative, takes care of that. Now, 1 plus the derivative squared is basically taking this ugly guy minus 1/2 and square it. I'm going to write that again. And there's a lot of algebra that you could go wrong here. If you take this guy and square it, you can square each piece. Negative 1/2 times itself is 1/4. And 4 minus x to the power of negative 1/2, if you square it, you essentially multiply the powers. And now you get 4 minus x to negative 1. And now I'm doing some style points on it. And I'm going to call it that. This guy might look okay to you, but he is not going to be very nice looking when I stick it inside this square root. So I need to do more work on this guy. So it's more algebra. How do you think I can combine these two together? How would I be able to combine them? Again?
Quick question on that. Is it still under a square root, or did the square root go away on the very last line?
On this line here, oh, square root does go away. You're right. It's not a square root, it's just a 4 minus x. Okay, how do we get this fraction to come together? That's where we are now. So that is just says 4 minus x, right? Come on, you know the answer, I'm sure you do. How do you take 1 and add this ugly fraction to it? How do we combine them? What do I turn 1 into then that allows me to combine it? Maybe I should ask the question that way.
A fancy one with 4 times 4 minus x in the bottom and top.
Correct. Which now means I have a single fraction. And 16 add 1 gets me 17, take away 4x. So all of that work was just so I could find the best version of 1 plus the derivative squared. Okay. So the arc length, S, is going to be the integral from 1 to 4, 2 pi f of x, which is this guy, times the square root of what we just found. Really ugly looking, but it's going to become much nicer. Can you see anything that we could do with this square root that might make it a little bit friendlier with what's going on?
Multiply the 2 square roots, canceling out the 4 minus x.
Correct. So to show how that happens, if you've got a square root of fraction, can't you split it by separating the square root in all the pieces? So square root at the top, square root at the bottom, square root of the other thing at the bottom. And just like you were saying, don't those square roots cancel? Well, by the way, doesn't that 2 cancel with this guy? So now what I'm looking at is a pi, the integral from 1 to 4 of just that. So this question didn't need a U sub. It did need algebra, which is like the third situation. So where are we off to now? Well, I'm going to rewrite this guy as 17 take away 4x to the power of half. And I could do a U sub on that if you want to, that's fine, but I'm just going to take the shortcut. And what the shortcut says is that you can basically treat this as if it was x to the half. So you add 1 to the power, and then you divide by the new power. And what do I do about the -4? I don't ignore it, right? It's a kind of chain rule situation in a way. How do you deal with the -4? What does it give me here? Any takers?
Would it be -1/4?
You nailed it. Yes, it would be. All I'm going to do here is tidy this up, and it's a mess. It's -1/6 pi. And this fella, I'm going to rewrite him. Oops, from x equals 1 to x equals 4. This fella, I'm going to rewrite it as 17 take away 4x cubed. And it's all to do with making things look pretty. So 3/2 is the square root of something cubed. These two multiplied together and give me -1/6. Now I should be able to plug in some numbers. If you plug in 4 here, you get essentially 17 take away 16, so it's 1. Cube root of 1 is 1. Subtract. If you plug 1 in here, you get the square root of 15 cubed. Now if I multiply this out, you get -1/6 pi plus 1/6 pi, and I'm going to call that guy 15 square root of 15. And there's my answer. And I could pull it to 6 pi, I guess. I didn't need to do that, but darn it, I got a bad cold. I hope I'm not bursting your ears. Get some oxygen here. Yeah, I know if I was a horse, they would have shot me by now. I got so many things wrong with me. Okay. I'm calling that one good. Are we comfortable with it? I know there's a lot of lines in it, but good. You followed it. I'm happy. So, see what else we can sort out. Okay. I haven't shown you one of these ones yet, have I? So, suppose I tell you that x is equal to y squared plus 1. And we want to do it from y equals 0 to y equals 1. I want to keep the numbers simple. But you've been told that it's rotated about the x-axis. Do you see that this question has everything in y's, but it's still being rotated about the x-axis? That means this formula gets used. Do you see how you can tell which of the two formulas need to be used when you rotate about the x? If the things are in x's, it's the top one. But if the information uses y's, as it does here, right, you do that one. So we are good to go. The surface area is going to be the integral from c to d, 2 pi y square root of 1 plus the derivative of y squared dy. So it's going to be the integral from 0 to 1, 2 pi y, and the square root of 1. Well, if you differentiate this guy, you get 2y squared. So because this one was so easy, I didn't do my, my usual write it all down kind of thing. I tend to leave that for the more awkward ones. I'm going to pull out the 2 pi again. And now we're looking at 1 plus 4y squared dy. Things looking good? What technique do I now need for this one?
Can I ask a quick question?
Yes.
On the second formula, why is it y on the outside? Why is it 2 pi y and not 2 pi g of y?
You would wonder that, wouldn't you? It makes sense. Well, technically speaking, it's this formula here converted. What is f of x equal to? Y. So they basically just took this formula and converted it into y. So you might say, well, how can 1 plus a derivative squared dx be the same thing as this fellow? Well, let me show you. Side issue. I'm going to write it down a little bit differently to make it a little bit more obvious. We have 2 pi, right? f of x, the square root of 1, but instead of the derivative, I'm going to call it dy by dx squared, and then I'm going to have a dx out here, right? And the other one is 2 pi. This guy is y, because isn't y equals f of x? Isn't there a direct transfer? Now, the square root of 1 plus, but I'm not going to call this g dashed of y. I'm going to call this dx by dy. Isn't that basically the derivative of x with respect to y? So that is the equivalent to him, dy. If they match, we only need to focus on these. Well, if you take 1 plus dy by dx and you square it and you do a dx, you will get 1 plus dy squared over dx squared. You don't need to know this, but it's a good question, so I want you to do it. You can think of these differentials and treat them in the same way algebraically that you would fractions. So what you get is dx squared over dx squared plus dy squared over dx squared dx. So you get dx squared plus dy squared over dx squared dx's. Do you see that the square root on this guy, if you do them separately, gives you a dx, and it cancels with the dx. So what you're left with is this guy. Now, if you take this one here and you go through a similar process, this one here also ends up being that guy. So essentially, these two formulas, as weird as they look and as different in some respects that they look, are actually mathematically the same formula. Now, I don't know if that helped or hurt the idea, but that's why.
Actually, that helped a lot. Thank you.
Okay. So if you didn't like what I just did, just forget the last 5 minutes, right? So back to this fella. What method are we going to use to integrate this ugly guy?
You said?
Yeah. U-subs are, in my opinion, U-subs are the most common method, right? Perfect squares, you haven't seen one, but the next one's going to be a perfect square, just to show you that. And then the third one is algebra. We've seen an algebra one. So if you differentiate this guy with respect to y, you get 8y. And the crossover, you get 8y dy. And then you divide everybody by 8y to isolate the dy's. So what do we have? We have 2 pi, the integral of a y, square root of a u, 1 over 8y du. And that cancel out to get your quarter pi. And the y's cancel out and you get that guy. Can I just dot that one? Isn't that pretty much obvious what you're going to do in the next few lines? Aren't you going to call that u to the half? And we did one almost identical in a different question. And you will get your answer with square roots and 2's and things in it, I suspect. So okay, just to dot that, because you finish that in your own time. Excuse me. Right, let's do a perfect square. We've got time for it, yes. We've got to find one. This is like question 10. We're going to do 1/2 x cubed plus 1/6 x to the -1. And we're going to do it from a half to 1. Actually, this question was written originally like that. But I like to pull out the fractions and then do the power thing. Okay? Now, this one is going to be type 1, that guy up there. But this is ugly. So I'm going to find its derivative. So it's 3/2 x squared minus 1/6 x to the -2. We all happy about the power rules, right? Multiply by the power, reduce the power by 1. Multiply by the power, reduce the power by 1. I'm now going to do 1 plus the derivative squared. So it's 1 plus 3/2 x squared. Take away 1/6 x to the -2 squared. And you're going to trust me on this, but if you FOIL this out, you get 9/4 x squared. Take away a half, take away a half, oops, sorry, take away a quarter, take away a quarter, plus 1/36 x to the -4. And now we get that guy. So far, so good. Now, from arc length questions, when you see 3 guys and they look sort of like this, what should you be thinking is happening? Algebraically, what should you get out of this situation?
A perfect square.
You should. Well, that guy gets you 3/2 x, and this guy gets you plus 1/6 x to -2 square. Are you happy about where the terms came from? Square root this guy, square root that guy. That means this guy is a perfect square. Like I promised, right? You do get questions with perfect squares sometimes. So the arc length formula is going to be the integral from the start of 1/2 to 1, 2 pi, the original function f of x, times the square root of this guy dx.
Would it be 3/2 x squared? Because the 9/4, it would be x to the 4 once you FOIL it.
Yes. Yes. Now, pull out your 2 pi. I have 1/2 x cubed plus 1/6 x to -1 times the square root of a perfect square dx. What do you think I should do next? We're still on algebra.
Would you FOIL?
You would indeed. And you know what I'm like? So these two guys get me 3/4 x to the 5. These two guys get you plus 1/12 x to the 1. I know you don't write ones, but I am. This guy gets you 3/12. 3/12. Yeah, let's leave him as 3/12 x to the 1. Again, you don't need to write the 1. And this guy gets you a 1/36 x to -3. As far as you can tell, did I do that okay? Okay, assume that we have then. So you're going to get 2 pi, the integral from 1/2 to 1 of 3/4 x to the 5. If you add these together, you get 4/12. 4/12 is just another way of saying a third. And this guy looks like that. And at this particular point, I'm going to do a dot, 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 dot. Would you agree that's just a very ugly power rule with some really ugly fractions? But won't the calculator do most of the heavy lifting for you? So you don't need to be too worried. Are we good? See what else we can do. Yeah, go for it. This one is like question 11. I'm not allowed to be sick because we got too much important stuff to do. So, but the good news is you can't catch anything over the internet. Now, if I was in class coughing a lung up, wouldn't some of you quite naturally be a little bit worried? But you don't need to be here. Okay. In the way that this information is being done, and we're still doing a rotating about the x-axis, are you happy that it's this formula? Are you comfortable this is the one we're going to use? Agreed? So, since this is ugly, I'll do its derivative. Oh, excuse me. Power rule. multiply by the power and reduce the power by 1 times 2y. Are you happy about where the extra 2y came from? Chain rule. Right. This horrible mess here, let's tidy up before I go any further. There's going to be a y. Actually, don't they cancel? Wow, that's really nice. Wasn't quite expecting such good stuff. Now, if you take the derivative squared, then you add 1. We can square the first guy. And if you square a square root, you get that guy. And this fella, when you distribute, gets you that. Because I'm a picture straightener, you should write things in order. I wasn't expecting this, but I'm actually kind of happy that it happened. Why am I happy that that's actually what all this horrible mess inside the square root looks like?
It's a perfect square.
It is. And as far as perfect squares go, would you agree it's one of the easier ones to do? So we can now do S. And S is going to be the integral from start to finish, 1 to 3, 2 pi y, followed by the square root of the ugly guy inside the square root, which is him, dy. But he's actually not that ugly. Because don't you just get that? What I would do next is pull out the 2 pi and distribute the y's. In the big scheme of things, would you agree that's a very nice polynomial power rule? And it should come out really nice. Okay, so for the last question today, let's try something. Do you all recognize that equation? Equation of a circle, center of the origin, radius r. Now I'm going to draw only the top half of that circle. So it would go from negative r to r. And I'm going to rotate it about the x-axis. So far, so good. Now, if I did rotate half a circle, wouldn't I get a total sphere? Agreed? Does anybody know what the surface area of a sphere is? Because I'm actually going to prove it. What is the surface area formula for a sphere? It's a pretty rare one, so I'd be surprised if you know it, but it'd be great if you did. Would it surprise you to know that the surface area of a sphere is just 4 circles worth? Kind of amazing, but that's the formula. So let's prove it. The surface area is going to be the integral from negative r to r, 2 pi f of x times the square root of 1 plus the derivative of x squared dx. Except this formula isn't written down as y equals an f of x. So let's see if I can make it. Would you agree that it's that guy for y squared? So won't y just be the positive, because it's the top half of this guy? So y is going to be r squared take away x squared to the half power. Its derivative is 1/2 r squared take away x squared to the negative half power times the derivative of this, which is negative 2x. And so you end up with negative x r squared take away x squared to negative 1/2. If you 1 plus it squared, I'm not sure if I'm going to have enough time now to do this, but I'll try my best to do it. Square that guy, you get x squared, and square that guy, and you get negative 1. So I'm going to call this guy 1 plus x squared over r squared take away x squared. Now this has happened today, hasn't it? Where we had a 1 plus a fraction. And didn't we just basically turn that into him? So we have an r squared take away x squared over r squared take away x squared plus an x squared over r squared take away x squared. And all you're left with is r squared on the top and r squared take away x squared on the bottom. So it actually comes out quite nice. So S is the integral from negative r to r, 2 pi, this guy, times the square root of this guy. I think we'll make it. I think we've got enough time to do this. It's going to be the integral from negative r to r of this guy. Square root of that guy is r. Square root of that guy is this guy. Oh, come on. Is that not pretty or pretty? It's 2 pi, the integral from negative r to r of r dx. If you integrate a number, you just stick an x next to it. And it's going to be from negative r to plus r. And x equals r gets me r squared. Take away negative r squared. And that gets me 2r squared, 2 times 2, 4 pi r squared. Now, if you'd done that 400 years ago, you would have been considered a genius. Because what we've done here, haven't we proved from calculus that the surface area of a sphere is 4 pi r squared? Instead of just being told it in a book somewhere, where the heck did that come from? We've actually proved it. In fact, couldn't we find the surface area of any old shape that we wanted to if we had enough time and the math came out nice?